Hello everyone, welcome to Nevin's Data Lab. This being the first video of the channel, I would love to dive into linear regression, which is one of the simplest but most powerful tools in machine learning. So what is linear regression? Linear regression finds the best straight line relationship between the inputs and the outputs. So let's say we have a data like this. So if we apply linear regression correctly, we will get a straight line like this that passes through almost all the data points, giving us the giving us the minimum error. So the equation of this line would simply be y is equal to wx plus b, because this is a straight line where w is the weights and b is the bias. Uh, so our goal is to basically find the best values of w and b such that the error between the points is the least. Now let's talk about how we actually find these best values for w and b. This is where gradient descent comes into place. So gradient descent is an optimization algorithm that allows us to minimize the error in our model. If we plot the graph of errors of all possible best fit lines, like let's say in this graph I have plotted multiple lines, and if we plot the errors of each of these lines, we will get a graph something like this, with the least point of error being our best fit line. So for finding this least possible error, we will initially take a random line, let's say this one. So the error of that would be somewhere around here maybe, and we will calculate the gradient of that particular point in this slope, in this graph, and we will move towards that direction of the slope. Like let's say this would be a positive slope, so we have to go towards the left. In the same case, if we had a negative slope, we'd move towards the right, and the amount that we move is based on the learning rate. Now, before we dive into coding, there are some things that we have to keep in mind. Those are the assumptions of linear regression. So if these assumptions don't hold, then linear regression might not be the best choice. So what are the assumptions? First is linearity. That is the relationship between x and y should be a straight line. What is x? X is the input data and y is the output data. So let's say in this graph, if we don't have like a linear trend, then we can't apply linear regression. Next is independence. So the observations should be independent of each other. That is, they should not be dependent on each other. I mean, let's say, for example, in a time series model, each data point would be dependent on the previous data point. So in that case, we can't use linear regression. Next would be homoscedasticity. It sounds like a weird term, but it's actually very simple. Let's say we have a data like this, in which the variance is like uh, lower in the beginning but increases as it goes by. So basically there is no uniform variance, like the variance is constantly changing between, I mean, in this direction. So in that case also we cannot use linear regression. Next would be the normality of errors. This is nothing but if we plot the errors of the best fit line, I mean if we plot the errors of each data point across the best fit line, we should get a normal graph. Now let's implement linear regression using just Python, no fancy libraries, just NumPy. Move on to the code. So let's start with the linear equation of the line. Linear equation of the line is nothing but y is equal to wx plus b, where w is the weight and b is the bias. Next, what is the loss function? In this case, our loss function would be the mean square error, which is nothing but y hat minus y the whole square. What is y hat? Y hat is nothing but the predicted value of y. Next, you can initialize some parameters. Let's say x is equal to mp dot random, not random. And let's say we have like 100 data points. So we have to like first initialize, I mean, first import numpy as well. Next, we can say y is equal to, let's say, 4 times x.
plus some other random value, and we can initialize our W and B as 0. So basically, if we do this calculation right, if we implement our code correctly, the value of W at the end should be close to 4, and the value of B at the end should be close to this random value. Okay, let's start with the gradient descent function. Gradient descent. So what we have to do is basically calculate the gradient of the loss with respect to W and with respect to B. So what was the loss? Loss is basically this y minus y hat. Let's say just rewrite as y minus y hat. And y hat is nothing but wx plus b. So if we want to calculate the gradient of this with respect to w, let's say dl by dw, this is equal to this would be minus 2 times x times this whole thing. And similarly, we can do it for with respect to b, and in that case, this won't be here. So what we want to do is we want to calculate the total gradients, like the average of the total gradients for each data point. So let's say we iterate through each data point. And we want to calculate this. Instead of x, we'll have to put xi, and instead of y, we'll have to put yi. Okay, and this is initialization, so we'll just set it to 0 for now. So what we are doing over here is we are calculating the total gradients. And since this is the total gradient, we'll have to take the average. So this is equal to this by length of x. Similarly, for b, this is equal to b by length of x. And we can calculate the new values of w and b. W new is basically w minus learning rate into this new value. So let's set, okay, we'll first have to take all the values. WB learning rate. Let's set the learning rate as default value to 0.1. So W new is equal to this. Similarly, B new would be equal to B minus learning rate times this thing. And we have to basically return W new comma B new. Now that we have written the gradient descent function, we can iteratively make updates now. Like let's say if we run it for like 1,000 epochs. What we have to do is we have to calculate the gradients. W comma b is equal to gradient descent of this thing. Yeah, okay. Next is y hat would be equal to this w that we got from the gradient descent function times x plus b. And the loss would be y minus y hat square. And since this is like a vector, we'll have to take a sum and then divide it with the length of x so that we get a scalar value. And we are taking the average of all the errors in this case. And let's just print this. Um, for epoch loss. Ideally, everything should work perfectly. And if it's correct, the value of B should be close to 4 and the value of W should be close to 4 and the value of B should be close to this random value. Let's run it and check. Okay, there is some issue somewhere. Mhm. Okay, so I found the error. I mean, the silly mistake that I was doing. Like for each data point, we'll have to like collect the total value of the derivatives, and that's why we are dividing it with the length because we have to take the average of the full gradient. So now if we run this, we can see that the value of W is close to 4, like we wanted, and the value of B should, I mean, it should be close to some value, which is a random value. So that's it for this video, guys. Thank you so much for watching. If you like the video, please like, share, and subscribe. See ya.